Okay, welcome to the class. Today we're going to complete the last piece of Unit 2, which is to use normal approximation to binomial distribution. Usually, the normal distribution is used as approximation to the binomial distribution when NP and NQ are both greater than 5. That is, for a binomial distribution. Do you still remember what a binomial distribution is? Okay, for a binomial distribution, we have two parameters, n, p, right? And q is actually n minus p. When we have a binomial distribution like this, and at the meantime, when np is greater than 5 and nq is also greater than 5, then we can use a normal distribution to approximate this binomial distribution. Okay, I'll show you why this can be achieved. First of all, let's have a look at a specific binomial distribution. When n is 12 and p is 0.5, that means x yields to a binomial distribution. Two parameters are 12, 0.50. And then we calculate probability distribution. Of x. Okay, we use a table to illustrate the probability distribution of x. Okay, first column is possible values of x, which is 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And the second column represents the probability of x being each value. Okay, according to binomial formula, the probability of x being 0 is C12, 0, 0.5 to 12 times, and 0.5 to 0 times, which is 0.0002. Okay, the probability of x being 1 is C12, 1, 0.5. Sorry, this should be 0 here. 1 and 0.511, right? This value is 0.0029. Okay, and using the same method, we can calculate the probability of x being each value. So its probability of x being 2 is 0.0161, right? I will not list all the values. Let's have a look at this table. The table here lists the probability distribution of x with its corresponding probabilities. And then we can use this table to draw a diagram. Okay, the green bar chart, the green bars represents a histogram for the probability distribution of the table on the left. As you can see here, we can use a curve to approximate these bars, right? This curve looks like very close to the normal distribution curve, right? So approximately, we can use a normal distribution to approximate the binomial distribution as long as the conditions are met, which is NP greater than 5 and NQ greater than 5, right? Okay, let's see some examples of the real world problems using normal approximation to binomial distribution. Okay, I'll show you an example of how we can use such a conclusion to simplify our calculations. All right, let's see the first example. According to an Arise Visual Solutions job survey, 32% of people working from home said that the biggest advantage of working from home is that there is no commute. Suppose that this result is true for the current population of people who work from home. What is the probability that in a random sample of 400 people who work from home, 108 to 122 will say that the biggest advantage of working from home is that there is no commute? Okay, first of all, like most of the questions, we need to know what the random variable here. The random variable here is the number of people in the sample who say that the biggest advantage of working from home is that there is no commute, right? Okay, so let uppercase X denote such random variable. Okay, you can use X denote the number of people in the sample who hold this opinion. Then we know that X yields to a binomial distribution, right? Because the sample has 400 people. That means you conducted 400 trials, right? And in each trial, the probability of holding this opinion is always 32%. And after the 400 trials, we denote the number of people in the sample who hold this opinion is X. Of course, X here it yields to a binomial distribution, right? Okay, so N is 400, P is 0.32, Q is 0.68, right? And actually, it asks us to find a probability that X lies within 108 and 122, right? If we use binomial distribution to find this probability, that means we need to calculate X equals to 108 plus X equals to 109. And of course, X equals to 1 to 1 and X to 1 to 2. As you can see here, we need to calculate all these values, which are very time consuming, right? So here we can use a normal approximation to simplify the calculation. Okay, let's see how we can do this. Okay, we will not use binomial distribution here. Because this is very time consuming. So we do not want this method. So how we can use normal approximation to do this? First, we need to calculate NP to see whether conditions are met, right? Okay, NP here is 400 plus times 0.32, which is 128. NQ here is 400 times 0.68. Of course, this one is greater than 5. This one is greater than 5. So you can use a normal approximation. That means x approximately yields. We use this sign here to denote approximately yields to a normal distribution. Of course, we need to calculate the two parameters for the normal distribution, right? Okay. Okay, EX is and P is 128. Okay, next we need to calculate mu. Mu is root square NPQ, which is approximately 9.33. Then our x approximately yields to a normal distribution. With two parameters, 1 to 8 and 9.33. Okay, then the probability of x between these two values is actually approximately to x in this interval. Because we are using approximation, so we need to correct the intervals with lower limit minus 0.5 and upper limits plus 0.5. Okay, pay attention to this. These are very important. And then in order to look up the SND table, we need to convert x to standard normal distribution. Okay. Then this probability becomes which is 0.2637. Okay, this is a complete process of how we solve this problem by using normal approximation to binomial distribution. Okay. Pay attention to the correction here. This is a correction factor, which means upper limit plus 0.5 and lower limit minus 0.5. When you use normal distribution to approximate a binomial distribution, you need to do the correction factor here with upper limit plus 0.5 and lower limit minus 0.5. All right? Any questions? Okay, as you can see here, when we use normal approximation to do this problem, it's much easier for us to look at the table than to calculate the separate probabilities, right? The second method is much quicker. Okay. If you have no questions, let's look at the next example. Check 200 calculators. For each calculator, the probability of being a faulty one is 6%. Suppose X is the total number of faulty calculators. Find the mean and standard deviation of X. B. Determine the probability that 20 or more defectives are observed in the sample of 200 calculators using the following table if needed. Okay. Let's try to solve this problem by using normal approximation to binomial distribution. First of all, if you want to approximation to normal distribution, you need to calculate NP and NQ, right? Okay. Okay, let's solve the first questions first. Mean. Mean is before we solve the mean and standard deviation, we need to find that X here apparently yields to a binomial distribution. Two parameters, N is 200, P is 0.06, right? Because you conducted 200 trials, and in each trial, the probability of being success or being a faulty one is 6%. Okay, that means our Q is 1 minus P, which is 0.94. Okay, so A mu is NP, which is 200 times 0.06, which is 12. Okay, standard deviation, sigma, is square root of NPQ, which is 200 by 0.06 by 0.94, which is approximately 3.36. Okay. Okay, B. Use binomial approximation to normal distribution. First, let's check whether we can use approximation. NP here is 200 by 0.06, which is 12. Apparently is greater than 5. NQ here is 200 by 0.94. Apparently this is greater than 5, right? So X here approximately yields to a normal distribution with two parameters. The first parameter is mu, which is 12. We have already calculated, right? Second parameter is standard deviation to square, right? X yields to such a normal distribution. And then we want to calculate a probability that X is 20 or more than 20, right? So this probability now becomes, okay, remember if you want to use normal approximation, first of all, you need to do interval correction, right? Because 20 is a lower limit. Lower limit, we need to minus 0.5, right? There is no upper limit, so you can leave the upper limit of the correction. We only need to correct the lower limit here because 20 is only a lower limit. And then this becomes X equal to or greater than 19.5, which is standard normal distribution equal to or greater than 19.5 minus mu divided by 3.36, okay, which is in order to look up the table, we need to convert this to 1 minus that is less than 2.23, right? Then we can look up the table to find the probability of that is less than 2.23, which is and the final result we're looking for is 0.0129. Okay, any questions? Okay, any questions? No? Okay, let's see the last example. According to an estimate, 50% of people in the United States have at least one credit card. If a random sample of 30 persons is selected, what is the probability that 19 of them will have at least one credit card? Solve this problem by using normal approximation to binomial distribution if applicable. Okay, first of all, what is the random variable here? Apparently it's a number of people, right? So here let X denote the total number of persons who have at least one credit card. Credit card. Then we know that X yields to a binomial distribution, right? Why? Because we conducted 3 trials, and in each trial, the person having a credit card is always 50. So X here strictly yields to a binomial distribution. And then whether we can use a normal approximation, we need to check NP and NQ, right? NP is 30 by 0.5, which is 15. NQ here is 30 by 0.5, which is also 15, right? So here we can use normal distribution, normal approximation. To use normal approximation, we need to calculate mu and sigma first. Mu is NP, which is 15. Sigma is square root of NPQ, which is square root 30 by 0.5 by 0.5, which is approximately 2.74, right? So here X approximately yields to a normal distribution. First parameter is 15. Second parameter is 2.74 square. then the probability we're looking for is x being 19, right? Okay, because it asks us to use normal approximations. So the first thing is to use interval correction. Because if you do not correct the interval for any given single value, x being the single value, the probability is always 0, right? So first of all, we need to expand this. We need to correct this interval, which is x being 19 means x is within 19 minus 0.5 and 19 plus 0.5. Because 19 is a lower limit as well as an upper limit, so we need to expand 19 to a very small interval, which means 19 minus 0.5 and 19 plus 0.5, right? Okay, that means we need to calculate the probability of x within this interval. And in order to look up the S&D table, we need to convert x to z. That means left-hand side becomes this one. And right-hand side becomes this one. Okay, which is equal to okay. And by looking up the S&D table, two values are and then final result is 0.0498. This is a probability you're looking for. Okay, any questions? Okay. Remember that originally we are looking for a discrete random variable whose probability is the probability of the discrete random variable being 19, right? And if you want to calculate using normal approximation, you need to do interval correction, which means the original number 19 expanded to a small interval, which is 18.5 to 19.5. Understand? Okay, do you have any questions? No? Okay. If you do not have any question, let's make a brief review of the Unit 2, and tomorrow we'll take the test for the whole Unit 2. All right? Okay, so in Unit 2, what we have learned. First of all, we learned that what is a random variable? What are the types of random variable, right? Yes, first, what is a random variable? And what are the types of random variable? There are two types of random variable, right? The first one is called discrete. The second type is called continuous. Okay. Continuous random variable, in the number axis, there exists at least one interval that x can be any value in this interval. Otherwise, if the random variable is countable and discrete, it's called discrete random variable. Okay, second, we need to know how to describe a discrete random variable. That means description of discrete random variable. Okay, first we introduce the probability distribution of discrete random variable. We can either use a table which shows all the possible values of x, or we can use a bar chart to illustrate the distribution of the discrete random variable, right? Such as this. And then we introduce the expected values, or called expectation or mean of discrete random variable. Okay, the expected value of x is the sum of all possible values times the corresponding probabilities, right? And denoted with mu. And for any given discrete random variable, if we have a function of this discrete random variable, we can also calculate the expected value of this function, right? Which is the sum of all possible values of this function times the corresponding probabilities. Okay, and there are some properties of the expected value, such as first one, and for any given constant, the expected value is always itself. And for any given number of the functions, the expected value of the functions is expected value of function 1 plus expected value of function 2. Okay, third, we learned what variances is. Okay, by definition, variance of x is the expected value of x minus ex squared, which is denoted by sigma square. Usually we use a derived formula to calculate variance, which is the expected value of x squared minus the expected value of x as a whole squared, right? And fourth, we learned that what a standard deviation is. Which is SDX denoted by sigma. By definition is the square root of variance of x. Okay. Then after that, we have learned some specific discrete random variable. Okay. First of all, we learn discrete uniform distribution. Okay. Second, we have learned binomial. You can check your notes after the class. And then we have learned hypergeometric distribution. Okay. I will not list all the properties here. You need to check your notes after the class. Okay. And then after that, we have learned continuous random variable. First of all, you need to know how we describe continuous random variable. We use probability density function. Which is abbreviated as PDF. Okay. For any probability density function, for example, we have a probability density function of any shape. Okay, and we have two constants, A and B. The probability of x lies in this interval is the area between this interval. This is x, the probability of x in this interval, right? Okay, and after that, we only learn one specific continuous random variable, which is normal distribution. Okay, remember that normal distribution have a bell-shaped probability density function, and the symmetric axis is always its mean. And there is a 68, 95, 99.7 rule. You need to know what this rule means. And also, if X yields to a normal distribution with two parameters, mu sigma square, and then we can convert any general normal distribution by X minus mu divided by sigma. This new random variable yields to a standard normal distribution, right? For a standard normal distribution, we can check the SND table to find any probability that uppercase Z is equal to or less than any value. Right? And then today we have learned normal approximation. To binomial distribution. Under the condition of NP greater than 5 and NQ greater than 5. Okay. If you want to use approximation, remember you have to use interval correction in the calculation process, which means upper limit plus 0.5 and lower limit minus 0.5. So these are basically what we have learned in Unit 2.